This is the last stuff I'd like to talk about in this unit. Our test is next Wednesday. We'll take the balance of the time between now and next Wednesday, getting our material in order and listening to tech presentations. Thank you for starting us off so well with that. Here's a problem that I'd like you to think about. A person stands on a flywheel, and this is a top view looking down on this person holding that shot put, and this flywheel or merry-go-round or disc or whatever you want is bolted to the ground. Okay? The person chucks the shot put, and so the shot put gains a velocity that way because the force acted on it. I guess this drawing asserts that afterwards the person, and you can imagine that the person is attached by friction to the wheel. This asserts that in the final picture there's an angular velocity in what direction? So clockwise. Yeah. We wouldn't use tangential. We would talk about maybe a translational velocity being tangential. We said clockwise. Can you give me a synonym for clockwise for a direction of angular velocity, Justine? Into the board. Yeah, that's right. If I use the right-hand rule and curl my fingers around in the direction of that angular velocity, my thumb points into the board. So we consider clockwise and into the board as being exchangeable ideas, interchangeable. Okay, great. Here are some questions that I wonder if we could think about together. Let's say the system is the person and the wheel and the shot put here. It's okay? Did any external torques act on this system between this picture and this picture? Drew? I agree. No external torques. And so what? Henry? Yeah, so the angular momentum in the system should be conserved. Okay, what's the angular momentum in the initial picture? Robert?
0.
How do you know? I agree.
Because there's no motion.
Yeah, no motion, no angular momentum. At least not about that red axis there. Okay, so what is the direction of the wheel's angular velocity afterwards again? I think we said it already, but Christian? Clockwise into the page. Is anyone feeling upset at this point? You should feel a little upset. Drew? You see no angular momentum, and then you see this wheel has some angular momentum afterwards. How is this possible with no external torques acting, Danny? Are you saying that that shot put has angular momentum? In what direction do you think that shot put has angular momentum? Out of the board, because I think you want to be looking at no angular momentum total in this picture. Does anyone feel upset by what Danny just suggested? Matthew?
I just want to say, isn't the axis an external force?
Ah. You're right. I wasn't going to tell you this until later. But it is true that during the throwing of this shot put, this bolt or this axle or whatever does exert a force on the wheel. If it didn't, then the force by the shot put on the person wheel would accelerate the person wheel down the page. Everybody okay with that?
Yep.
So there must be some force that this bolt or this axle exerted on the wheel. Does that force exert an external torque on the system?
No.
Why not?
Because the external torque.
Yes.
Like you mean, okay.
That is my question.
Yes. The person wheel system. Yes. The person wheel and the axis system.
Well, let me take a step back again. Yeah. Between this picture and this picture, did an external force act on the system of the person wheel shot put? Kevin? No. I think it did. An external force did act. It's the force by, well, something about the ground exerted a force on something about the wheel. Because if it didn't, then the wheel would start translating that way. But it didn't start translating. So yeah, something about this axle exerted an upward force. Robert?
Well, because the force is exerted at the center of at the axis of rotation, there's no torque because the r vector would be 0.
Ah, right. Was there an external force acting on the system? Yes. Was there an external torque? No, because that force acted where? At the axis of rotation. We'll return to this idea 4 or 5 slides from now. But good spotting, there was an external force. It just wasn't an external torque because it acted at the axis of rotation. Henry?
So if we have an external force acts on the axis of rotation,
Mm-hmm.
then wouldn't that force need to be continuous in order to have continuous change in the velocity of the object? Because we talk about the idea of only like the normal component of acceleration,
Mm-hmm.
which is like basically you can consider as a normal component of the force is acting to change the direction of the change. But wouldn't that force need to be continuous in order for the wheel to continue spinning?
I think the question relates to when is there a force by the ground on this object?
Right.
And here's my answer. The whole time the person is exerting a force on the shot put,
Okay.
that force by the ground on the wheel is canceling the force by the shot put on the person. After the shot put has been released, then I think there's no more force on the wheel by the ground.
Right.
If there were, then it would be accelerating the wheel on the ground. Okay, so I think we've looked more closely at this question. Did any external torques act between here and here? No, even though some external force did act. So angular momentum has to be conserved. No angular momentum here. There is angular momentum of the wheel here. And Danny, you asserted that this translating point mass has angular momentum? Or you asserted is strong, but you floated that idea. And yes, that has to be the case. The shot put has to have some out of the board angular momentum afterwards. And so here's the lesson of the day. A point mass translating can have an angular momentum about a particular axis. This should feel upsetting to you right now. Angular momentum you associate with going around and around and around and around something, and it's not true that this shot put is going around and around and around and around and around this axis. So I'm going to do 2 things that will hopefully give you some sympathy for the idea that this mass can have angular momentum about that axis. Here's the first thing I do, and Jasheen, follow me, if you will, on the camera. Everybody, please hold out your arm and point it at me, and keep pointing at me as I move. Okay. See how I was just traveling in a straight line, yet I did have some aroundness of you. Would you have ever stopped moving your arm as I kept going in that direction? Would you ever have stopped turning your arm? No. In a sense, I was you can stop now. In a sense, I was turning around you. I wasn't turning around and around and around and around and around you, but a vector from you to me was rotating, and as I continued traveling in a straight line way, it would have never stopped rotating. Drew? You note that something is decreasing, and why does that bother you? You expect it looks like something is decreasing, but you want something having to do with angular momentum to stay constant as I do this, because if we're in space and I'm just like floating along in a Newton's first law way, no external torque is acting on me, so my angular momentum shouldn't be decreasing. We will resolve this paradox in the next slide. But you're right, the punchline is that my angular momentum will be staying constant. So I told you that it should initially be upsetting at the idea that a translating point object could have angular momentum about an axis. But then I hopefully motivated the idea that there was some aroundness of you as I walked in a straight line. Here's another demo that I'd like to do to give some sympathy to the idea that there's some angular momentum even when things travel in a straight line. Danny, would you stand here facing this way with your left elbow like this? Great. And translate a little bit to your right. Great. And I'm going to do the same thing. And we're going to walk towards each other in a straight line way. Ready? Go. Yeah, great. Thank you. And of course, we were walking and there was friction. But if we were two astronauts, like Sandra Bullock and George Clooney did that like all the time in the movie Gravity, where they would, yeah, let's do it one more time. Straight line, around and around and around and around and around. Great, thank you. So if we were astronauts, then clearly in the Danny Siegel system, no external torques were acting. We clearly ended with some aroundness, with some angular momentum. But if no external torques acted, then we must have started with some aroundness. There must have been some aroundness even when we were walking just in a straight line. So that's the second thing I will say to hopefully give you some sympathy for the idea that there can be angular momentum even when objects are traveling in a straight line way. Drew? Good question. Well, and in fact, I'll see you that and raise you, let's make a quantitative expression for how much angular momentum is associated with a mass m at a velocity v.
Yeah, a question. Is angular momentum defined as the amount of rotation? Because momentum is defined as the amount of motion.
I'm not sure I'm ready to get behind momentum is the amount of motion.
Right.
Momentum is mass times velocity. We defined it that way not because we proved that it must be so, but just we found out that when we had this quantity, mass times velocity of an object, we had some physics to say about it that was explanatory and predictive. You might equally well say, well, kinetic energy is the amount of motion, but I'm not sure I agree with that either. 1/2 mv squared is a quantity that if you explore and analyze situations, looking at kinetic energy can help you explain and predict about some situations. And so angular momentum too, we can maybe empirically, if you like, arrive at the idea that defining the I omega of a rigidly rotating object can help us. And now our lesson today is going to be about quantifying and determining the direction of the angular momentum of things that are traveling in straight lines like they are translating point objects. Did we talk, incidentally, about how the conservation of momentum and the conservation of angular momentum and the conservation of energy are big deals?
Yes.
Can anyone remind us what were some things that we said about that? Anyone I haven't heard as much from today? Kevin?
They all apply to quantum mechanics too?
Yeah, that in quantum mechanics, those concepts turn out to be pretty useful. And not just at the tiny scale, but also, what's the realm of physics that deals with the biggest, largest masses? Yeah, cosmology, general relativity talks about, what happens when you have huge scales of speed and mass. And conservation of momentum and angular momentum and energy apply in their own ways in general relativity as well. Here's something that's fun, and I'll tell you. I'm going to leave out the details of the physics because it's not something I have mastery of myself. But physicists connect these 3 grand conservation laws to 3 fundamental symmetries. Each conservation law relates to a symmetry.
There's a very messy one.
Is there? Cool. you would expect that the physics that apply to this location is the same as the physics that applies to this other location. Therefore, conservation of momentum. I don't know the details of the therefore, but people do. And the idea that the physics here should be the same as the physics here gives rise to the conservation of momentum. The idea that the physics of this orientation should be the same as the physics of this orientation gives rise to conservation of angular momentum. Would anybody like to guess the symmetry that gives rise to the conservation of energy? Robert?
Time symmetry.
Time. Yeah, the idea that the physics relevant to now should be the same as the physics relevant to now, therefore conservation of energy. I don't have the details, but I don't know. I don't know the humanitarian there's maybe a humanities payoff. I feel like there's poems that a person could write about that. I am regretful to have to flub the details on the new state of matter. But I think I do remember that it had something to do with some symmetry issue or breaking. Anyway, conservation. It's a big deal. We had said this about torque. We had said that torque was kind of like the rotational analog of force, but it was less analogous than position was to rotational position. But torque is more different from force than angular velocity is from velocity. This is what we said about force and torque. Anyone going to guess the expression that we're going to adopt for the angular momentum of a translating point object?
The what?
The angular momentum of a translating point object. My angular momentum about you as I go like this. What do you think it might depend on? Robert?
The radius.
The distance that I'm at from you. Okay, good. Yep. Henry? Yeah, something about the angle. Anything else? Danny? My speed. Anything else?
Use the bathroom, sorry.
You may use the bathroom? Correct. One more thing that the angular momentum of a point particle depends on. My mass. Yeah, that's right. Anyone want to guess the expression that incorporates the distance, the angle, my mass, and my velocity about you? Robert?
M the sine of theta.
And you've left out one more variable.
Which is
It's r, my distance from you.
your distance from me.
Yep. Drew? You're very close. What two vectors? What is m scaled by v? It's p. Yeah, that's right. When an object moves with a momentum p, and there's an axis, you can define an r vector from the axis of rotation to the location of the object, or to the location of its velocity vector. And the cross product of r and p describes the angular momentum. So that this is the answer to your question about the direction of angular momentum. And it also includes the idea that the magnitude of angular momentum depends on the distance of the object from the axis, the sine of the angle between r and theta, the mass of the object, and the velocity of the object. Nice.
Is this true even if the object's not? Can we use this for the man on the wheel himself?
Great question. If you have a wheel, what we said yesterday is if you want to write down an expression for the angular momentum of this wheel, you can. I omega. When you have a rigid rotating object, rigid as in attached every bit is attached to each other. And it has an angular velocity omega. You can still use I omega as an expression to capture the whole angular momentum of the situation. If you were to treat every little bit of this as a little dm mass with a vector velocity and a vector momentum, you could add up all of the individual r cross p angular momenta to get the whole angular momentum of the whole thing. But when you have a rigid rotating object where something clearly is going around and around and around, then yeah, use I omega. So the answer to your question is yes, you could say this about all of the bits of mass in the man on the wheel, but better to say this. For example, the angular momentum of the ball around that blazer's finger, I omega or r cross p? Question? I omega. The angular momentum of that hockey puck shot and with this instantaneous velocity about that axis, I omega or r cross p? R cross p. Ah, yes. Haha. Congratulations to us all. Everybody, take a few minutes, and I'd like you to write your way to an expression for the angular momentum of this mass about that axis and this mass about this axis in terms of m, v naught, a, and b, please.
At that instant.
At the pictured instance. So here's one situation where I'd like you to write the angular momentum. Here's a separate situation.